Okay, a couple announcements before we get started. Your exam for Module 1 will open today after class ends and close tomorrow at 12:15. It's 30 questions, multiple choice, A, B, C, or D. 2 points per question for 60 required points. And then questions 31 to 40 are bonus questions. So those are also worth 2 points apiece. So that's a way that you can sort of pep up your score and is a baked-in curve for the exam. Any questions? So I assume everyone's able to log into their zip grade at this point in time and see everything. Yeah, let's just, any questions before we get into it? So we had left off on this slide here talking about how substitution of different functional groups affects the physical properties. So there's still a couple things we need to learn about functional groups and bonding patterns for the exam today and as we close out Module 1. So we'll look at how do other heteroatoms influence degrees of unsaturation. So we'll use that, draw some constitutional isomers, how we differentiate them using uniqueness. We'll talk about sometimes in the bonding patterns you don't have a neutral atom. You have an atom that's charged, +1, -1, how does that arise? And then another structural feature called resonance. And with that, we'll pretty much know what we need to know moving forward into Module 2. So to recap, this slide, how does the functional group affect physical properties? And as I stated, in yellow, green, and blue, we're just increasing the number of carbon atoms. So the first column are the alkane functional group. The next column, you're substituting. So when I use that word, so if we're starting with methane, CH4, we're going to take an H and then substitute it for some other functional group. So column 2, you're substituting for a bromine. Column 3, you're substituting for a hydroxyl that makes alcohols. And now the difference in the last 2 columns, it says OS2, OS3. OS means oxidation state. So the hybridization of the carbon, so you have sp3, sp3. In these 2 columns, the carbon is changing oxidation state and it's being oxidized. And what I mean by that is oxidation state is when you look at a carbon and you count the number of bonds to a heteroatom. So an alkyl halide and an alcohol both are at oxidation state 1. An aldehyde, so methanal, which is shown here, all you're doing is counting those number of bonds to the oxygen, so you have 2. So we say it's oxidation state 2. Carboxylic acid, you have the carbonyl group plus the sigma bond to the oxygen, so that's 3. And to help understand reactions when we start learning them, I organize the class in terms of oxidation state. So we learn how to make specific oxidation states on carbon, and then we'll learn how to go back and forth between oxidation and reduction. So the main thing we want to understand now is, for example, in ethane, we substitute for bromine or hydroxyl, and then how does that influence the changes in what we see in the melting and boiling points. And so that relates to the non-covalent interactions, hydrogen bonding, donating, accepting, and then all the weaker ones like van der Waal radii and induced dipole interactions, things like that. So any questions before we move on to degrees of unsaturation with heteroatoms? So we saw before that CnH2n plus 2, that's the molecular formula for an alkane. So carbon is fully saturated. And that gives us the maximum amount of hydrogens for that number of carbons. What is new to us now is when we start putting nitrogen, oxygen, or halogen into a molecular formula, how does that influence the hydrogen count? And then from that, we can calculate degrees of unsaturation. So if you're given a molecular formula with a nitrogen, oxygen, or halogen, what do you need to do? Nitrogen and phosphorus are in the same group. So we have CNOF, so that's a period. Then below that is the next period, silicon, phosphorus, sulfur, chlorine. So periods run horizontally, groups run vertically, so this is a period. If you have those elements, they will subtract a hydrogen from your given molecular formula. Oxygen and sulfur do nothing, so no change. All the halogens, fluorine, chlorine, bromine, and iodine, will add to your hydrogen count. So for your n number of carbons, you're determining the maximum number of hydrogens. Then from your given molecular formula, if you have a heteroatom, you have to revise your given formula before you calculate degrees of unsaturation. So those are the rules. Let's sort of do some examples so we can understand what we need to do. So in Monday's lecture, I showed you the structure of gifritoxin. And when you're given the structure, so degrees of unsaturation, you visibly identify and count the number of pi bonds plus the number of rings. But now on this slide, you're not given the structure. So you don't have that information. But we do have the molecular formula. So how can we use the molecular formula to calculate degrees of unsaturation? So we have C19H29NO. So our N is equal to 19. So the total number, the maximum number of hydrogens, if we use CnH2n plus 2, should be 40. You see in your given formula of gifritoxin, what's odd about that, or what's weird, is you have an odd number of hydrogens now. So if you took 40 and subtracted 29, you would get 11. You can't divide 11 by 2 and get an integer. And so that's why you have to consider now, how do these heteroatoms influence the hydrogen count? So if we just look at it, we scan across, we said that nitrogen is going to subtract a hydrogen. Oxygen is going to do nothing. So we say nitrogen -1. Above the oxygen, I'm just going to write a 0. It doesn't do anything. So this actually becomes C19H28. And that's what we then use to do our organic chemistry math. So max number of hydrogens minus C19H28. So I'll just say like revised. And so there we would get H12. And again, a degree of unsaturation is defined as H2. So we just divide by H2 and that gets us 6. And if I remember correctly, those 6 degrees of unsaturation, you had a triple bond, a triple bond is 2 pi bonds, you had a double bond, that's 1, and then we had rings. We had 3 of them. So that gets us our total of 6 degrees of unsaturation. The reason I'm presenting this to you in terms of learning this, you have to be sort of versatile, and you can look at the structure and count the rings and pi bonds. So the structure is a piece of data, but say, for example, you do not have that piece of data. You have this unknown substance. You're able to determine the molecular formula through some means. Then you figure out the degrees of unsaturation. And then as we move into Module 2, you'll be presented with other types of data that you can then say, okay, of these 6 degrees, I know one of them is a triple bond based on the data I'm seeing. And so what you're doing is like building up your confidence level and a claim that you make to what the structure could be.
So how do you tell from it just being 6, that it's the like bonds and rings?
So that was from the structure we had shown. So we can make that connection. So as we move forward into the next slide, and maybe a little bit later if we have time, I'll show you how you bridge that gap. Like, how do you know? So we can do another one. So this molecule called efavirenz, again, the structure's not up there. We're just given the molecular formula. And then we can scan across so that everyone's on the same page. In the molecular formulas, carbon is always listed first, hydrogen second, and then any other heteroatoms are listed in alphabetical order. So Cl is chlorine. It's not chlorine and then iodine. So Cl, that's chlorine. So as we scan across, we can just make some notes. We know that halogens will add. So we have 1 chlorine, that's +1. We have 3 fluorines, that's +3. Nitrogen subtracts, so that's -1. Oxygen does nothing. So the chlorine and the nitrogen sort of cancel out, +1 and -1, and then that will revise our formula to C4 H9 plus 3, that would be H12. And so N is now 14. So we get what? 28, 30. So for 14 carbons, the maximum number of hydrogens is 30. And then we just take our revised formula. That should get us H18. And we divide by the definition of a degree of unsaturation, H2. And so that would get us 9. So C. But, you know, as the question was stated, if you didn't know any structural features, 9 degrees of unsaturation is a lot, right? Because if you think of all the combinations that can be, it can be 9 like alkenes, it can be, you know, 9 rings, or you have all these different possibilities of those things. Any questions? Still see some writing, some photo taking, so I'll give it a couple seconds. So let's start. There's like the next run of slides are all of this form. We're definitely going to do this one like fully and completely. The ones after I'm going to probably leave for you to do by yourself, just so that we can get to the rest of the material today. If there's time, we'll come back to them. So we have a molecular formula. And what we want to do now is determine the degrees of unsaturation. Once we do that, we want to expand that into different constitutional isomers. And then we want to think about the uniqueness of the carbon and hydrogen sets so that we can differentiate them. So we're given C3H7Cl. Chlorine will add 1. So that becomes H8. Sorry. So N equals 3. So 2 times 3 is 6, plus 2, that's 8. Oh my gosh, I can't write today. So max minus C3H8 given / revised. And when we do this, we see that we end up with 0. So within that molecular formula, there are no degrees of unsaturation. So anything we propose, there's no pi bonds, there's no rings. So we have 3 carbon atoms. So there they are, 1, 2, 3. And now we have to stick a chlorine in there. And the most logical way to do that would put the chlorine at carbon atom number 1. And so you could say, well, we can also put it at carbon number 2. And at that point, we've shown structures that satisfy the molecular formula. There's no degrees of unsaturation, and we're pretty much done. You may have a question. I'm going to draw it over here. What about can I put chlorine at carbon atom number 3? You can, but it's the same as when you put it at carbon atom number 1. So one of the things you'll have to accept as fact, the difference between these two structures that I just drew, they're the same thing. One of them is just rotated. If you can imagine in your mind rotating at 180 degrees, it will then map onto that existing structure exactly. So they're the same. So we have 2 constitutional isomers of this chloropropane. This would be called 1-chloropropane. This would be called 2-chloropropane. But a more quantitative way of differentiating them would be according to the uniqueness. So for each one, how many unique carbons does 1-chloropropane have? It has 3. You have a CH2, a CH2, and then a CH3. Carbons 1 and 2, even though they're both CH2 groups, they're different. Because carbon 1 is bonded to chlorine. So carbon 2 has to be different. And then carbon 3, of course, is also different because it's now a CH3 group. So we could say that's 3. The unique sets of hydrogen also have to be 3. So that set is 2, that set is 2, and then that set is 3. So total 3 plus 2 plus 2, that's 7. That's your 7 total hydrogens. What about 2-chloropropane? So 2 unique carbons. So when you look at this molecule, there's a plane of symmetry that I'm drawing in blue here. Carbons 1 and 3 end up being the same. Carbon 2 is different. So again, even though the molecular formula has 3 total carbons, only 2 of them are unique. And the hydrogen sets will track that. And see how this number is 2? That means we're going to report 2 numbers here. So what should those numbers be? 6 and 1. And again, that's a total of 7. So going back to the first one, see how this number was 3? We report 1, 2, 3 numbers, that's 7. Yeah.
Do you always differentiate based off the original formula or the revised formula? Like, is there ever a situation where you would find 8 hydrogen? Because of the, like, how the halogen...
So yeah, when you do the uniqueness, you're always using just your given. The revised one, this is only for your degree of unsaturation calculation. So this concept right here, this uniqueness, if you understand how to do this, in module 2, the new thing is I'm going to show you data, and then you're going to interpret data to assign structure. So if I showed you a carbon NMR spectrum, and that carbon NMR spectrum had 3 signals, you could say it has to be this structure, because this has to show 3 signals due to the uniqueness. So that's the purpose of this right now. And then when we get into module 3 and we start learning reactions, these 2 structures those 2 structures are products of the reaction of taking propane and halogenating it. So the complicating part of this course is when you run a reaction, you don't just get one thing. Typically, you're getting more than one product, and you have to be able to differentiate them. So as I said, the next couple right here.
Yes.
So we're saying that we have 2 unique sets. So C1 is equal to C3. So this is a CH3 group. That's a CH3 group. So we count those hydrogens, 3 and 3, that's our 6. This carbon here only has 1 hydrogen. So that's our total number of hydrogens, 7.
Plus 2, but for this one, we didn't do that. It's still C3CH8.
So like right here. So let me, slides are for you to practice. If there's time left over after I get through everything else, we might come back and do some more of this. As you'll see, there's different heteroatoms in there. The degrees of unsaturation changes. And once you figure out degrees of unsaturation, again, it funnels you into certain functional groups. So like this one has an oxygen in it. So now you can start thinking, what functional groups have oxygen? And after you determine degrees of unsaturation, that will also help you as well. Can you have alcohols or ethers, aldehydes, ketones, so on and so forth? Slides so I can. Any questions? Yeah.
Where'd you get the 6 from? In the last one?
Where'd I get what from?
The 6. I got the ratio, standard ratio formula.
So we always use that for the maximum number of hydrogens. So for that molecular formula, it turns out that because we're adding this +1, that's what we're given. We revise it due to the chlorine. That becomes C3H8. And if we plug N equals 3 into this, that's going to give us C3H8. It just so happens that the molecular formula has no degrees of unsaturation. Yep. So a couple more things we have to get to in terms of understanding bonding patterns. One of them is formal charge. And this was the structure of AZT. And you'll notice on two nitrogen atoms, I've specifically shown there's a negative charge on that nitrogen and there's a positive charge on that nitrogen. See these other two nitrogens? There's no charge shown. So why does one have a minus? Why does one have a plus? The reason for that is those atoms are not in the neutral bonding pattern. So what do I mean by that? So here's our elements that we're building from: hydrogen, carbon, nitrogen, oxygen, fluorine. Below there is the group number. So that group number is important for us in this equation that's shown. So neutral is the neutral bonding pattern. So we know hydrogen forms one bond, carbon forms 4 bonds, nitrogen 3, oxygen 2, halogens 1. If you multiply those numbers by 2, we need to get to an octet. So hydrogen only forms one bond. So it has no lone pairs. So 4 times 2 is 8. So carbon's octet is met in the neutral bonding pattern. Nitrogen only has 3 bonds. 3 times 2 is 6. So 8 minus 6 is 2. That's one lone pair. And then the same for oxygen and then halogen. So what does that mean? So for example, if you look at water, see how water shows 2 bonds and then 2 lone pairs? That's what we mean by the neutral pattern. So atoms that are not in their neutral pattern, you have to calculate the formal charge. So Fc, that's defined as the group number minus the number of unpaired electrons minus 1/2 of the bonding electrons. So let's look at this nitrogen right here. I'm going to say formal charge on nitrogen. That's equal to, since we're dealing with nitrogen, it's group number 5. So minus the number of unpaired electrons. It's 2 electron pairs, but it's 4 total electrons. So 4, that's what we see there. And then minus 1/2. There's 1 bond, there's 2 bonds. So there it is. If we take 1/2 of 4, we get 2, and that would get us to 5 minus 6. That gets us to -1. And we can do the same thing for the other nitrogen that's plus. So group number 5. So as this nitrogen right here, as it's drawn, how many unpaired electrons are shown? None, 0. There's no lone pairs or electrons there. So 5 minus 0, minus now 1/2. So we have, I'll draw it in blue. we have this bond. So 1, 2, 3, 4. So that's 8 electrons we're going to put in that parentheses. So 5 minus 1/2 of 8, that's 4. That gets us plus 1.
Is this done by like an individual atom on the structure, or is it like a whole clump of them?
So this is something that, you as a student, if I didn't put the charges in there, you would have to recognize by visually scanning every atom in there, is this in the neutral bonding pattern? And so that's the sort of test you're applying to each atom. If it doesn't, the way I phrase it, if it doesn't look normal, then you have to go through this process. So I think we have some examples of this. Any questions? So a functional group I did not talk about last time is called the nitro group, and that's NO2. The compound shown is called nitrobenzene. And it says there's formal charges on the N and O heteroatoms. So notice I've put in the lone pairs of electrons, but I've not put any charges on anything. So we have to apply those rules and figure out what is getting what. So to maybe give you some clarity to that question, or hopefully not confuse you anymore, we said that oxygen in the neutral pattern has to show 2 bonds in 2 lone pairs, right? When you look at this oxygen right here in black, there's 1, 2 bonds, 2 lone pairs. So visually, that oxygen has to be neutral or no charge. When you look at this oxygen, it's not obeying that. There's 1 bond in now 3 lone pairs. So it can no longer be neutral. So if we calculate formal charge for oxygen, oxygen, again, we're doing CNOF. There's the group numbers 4, 5, 6, and 7. So oxygen's group 6. Minus 6 unpaired electrons minus 1/2 of the bonding electrons, that's 2. So 6 minus 6 is 0, minus 1/2 of 2, that's minus 1. So we can eliminate A and C. So just thinking about things, if oxygen's -1, what do you think the nitrogen has to be? +1. But we'll go through this calculation to verify that. So this is negative. And so again, when you're looking at this nitrogen, we said nitrogen has to have 3 bonds in 1 lone pair. It's showing 1, 2, 3, 4 bonds in no lone pair. So group number 5 minus 0, so no unpaired electrons, minus 1/2. We have 4 bonds, that's 8 total electrons. So that equals +1, so nitrogen's plus. And that would get us to D is the correct answer. I'm giving it away. Don't look. Close your eyes. So one of the things when you were learning about acid-base chemistry in Gen Chem was how water can auto-ionize. So the word is right there, ion. Ion means a charged species. So water is neutral. It will auto-ionize to form H and OH, and then those things will have charges. So the question is sort of a clue as well if you're thinking about the nomenclature. It says proton and hydroxide. So from your recollection of Gen Chem, hydroxide should have what charge? Negative. So things that end in IDE are typically negative. So hydroxide is negative, and so that, therefore, proton has to be positive. The take-home message is because you're starting with neutral, there's no charge. The ions you form, the sum of their charges still must be zero or neutral. So the answer for this one is also D, but if we say on this oxygen, so if you're given that structure, how do you calculate formal charge? So it's group number 6. So minus 6 total unpaired electrons, and then minus 1/2 of that shared bond between O and H, that's 2. So 0 minus 1, that gets you -1. And we represent that with just the minus inside a circle. So just to reiterate, because that O is minus, that H has to be plus. So plus and minus, that's getting you overall a net zero charge on that side of the equation. So what's tough about you as the student learning this, you're learning like a small part of this concept right now, and it's really going to relate to when we start learning about reactive intermediates. So we're going to learn about carbon that's negatively charged, a carbon anion, or a carbon that's positively charged, a carbocation. So we have to know how to do this in order to understand how reactive intermediates are formed. And again, that's later in the semester. But as part of understanding the bonding patterns, we need to know it now. So this is just a summary table that, if you're looking at structures, what are the neutral bonding patterns for the different elements? So you have number of bonds, number of lone pairs. That's visually kind of what you're looking for. If it doesn't resemble that, then it's either going to be plus or minus. So you can see maybe I'm going to use oxygen as the best example for this. So that's water, H2O. If the oxygen is plus charged, that means there's another bond to that oxygen. So now you have 3 bonds in 1 lone pair. And does anyone remember the name of that thing? Huh? Hydronium ion, yep. And we would say hydronium ion is protonated water. So you can protonate water by adding a proton, or you can remove a proton, and then that forms hydroxide. So that's 1 bond, 3 lone pairs. And again, IDE typically means negative. Onium typically means positive. So that the vocabulary can help you out a little bit in understanding these things. The same holds true for nitrogen and carbon with the number of bonds and the names as well. It'll give you a clue as to what, if there is positive or negative charge, how they're specifically named. So there's no like A, B, C, or D on this. I used to use this thing called iClicker, and then students would just like tap on the structure. So I'll just say A, B, C, or D. It says, which of the following does not correctly assign formal charge to the heteroatom?
A.
So it's A. Three bonds plus 1 lone pair of electrons should be positive. You'll notice with D, 1 bond plus 3 lone pair of electrons, that should be negative. Again, I've studied chemistry since my late teens, so I've been doing it for almost 30 years now. To me, I just look at it and say, is it neutral or not? Your best way of learning this is to run it through that formal charge equation. So when I look at structure A, I see 3 bonds to oxygen. In my mind, I say that looks weird, so I need to calculate some charge for it. Questions? So related to that, we've seen this nitrobenzene. We've calculated the formal charges. Now there's another concept we need to know called resonance. And I'm going to use this example. We have 2 oxygens. I've left one colored black and the other colored red. If you look at either of the right or left structures independently, you could say like on the left structure, that oxygen is showing 2 bonds to nitrogen, which means it would be different from the red oxygen that's only showing 1. But overall, in the molecule itself, those two oxygen atoms are equivalent. They're equivalent through this concept of resonance. And that's really just how we're looking at where lone pairs reside. If we're looking at lone pairs or we're looking at pi bonds. And so we calculated from before that the oxygen should be negatively charged. Carbon or nitrogen plus, but then you look at the right structure. Now you see that the black oxygen atom has the negative charge. So how does that happen? So we use this thing called curved arrows to show electron movement. So the arrow that I've shown here, that arrow specifically means resonance. It's a horizontal line with two arrowheads at either end. A curved arrow like this, it's a curved line with an arrowhead. Because there's two sort of parts to that arrowhead, that means two electrons are moving. There's also another type of arrow called a fish hook. And notice it only has one sort of part of the arrowhead. That just means one electron is moving. So the relationship of the two structures you see, if you had nitrobenzene in a bottle, it's one compound. It's not two separate things. Resonance is just a way to show you where you have charge density. And so on the left structure, I'm going to use this curved arrow to show that a lone pair from oxygen can form a double bond to nitrogen. So if we do that, we're going to break the existing pi bond to the other oxygen. And so that's how the black oxygen would then get the negative charge. And so we can do it the other way. And that just shows how the electrons are located within that functional group. The other thing I want to point out in resonance, when we drew those curved arrows, the only thing that's like moving are the electrons and then how we assign the charge. Notice I did not break or move any atoms around. The connectivity is still the same. We're not altering any framework or structural features. So resonance is just a delocalization of electron density through a pi bonding system. Electron density can be, you can have an excess of electron density or a deficiency of it. So, there's this term here, radical. Radical is when you use that fish hook. Radical just means a single electron. Typically, you have to have a pi bond in this. So resonance involves either 2 or 3 atoms at a time. So this molecule is called benzene. This is still benzene. And this was the resonance arrow. It's a very subtle change from the structure on the left to the right. But what is happening is the location of the pi bonds from left to right are different. That just means those electrons are delocalized across all 6 carbon atoms of that ring. Resonance, for the most part, we'll deal with it in organic 1, but really we use it a lot more in organic 2 to help explain reactivity. So this slide says, what is resonance not? So it's not the movement of atoms. On the left side, we have this ketone, and then we see a hydrogen atom. That's bonded to a carbon. And on the right side, that hydrogen atom has now been bonded to oxygen. We've moved an atom, so that's not resonance. This specific example has a name. It's called tautomerism. It's a shift of, so H shift from C to O. So resonance, you can't do that. So it's a separate process with a different name. So ketone going to an enol is not resonance. And so notice this arrow is not resonance. Again, as we progress through, these modules, organic chemistry uses a lot of different types of arrow. And the arrows are conveying to you what process is occurring. Another example of that is seen in AZT. The Z in AZT is related to that N3 functional group. That's called an azide. And as you see, we calculated the formal charge on nitrogen before, and the curved arrows here allow for resonance within that azide group, where that negative charge is shifting from one nitrogen to the end nitrogen. Because the electrons move, the bonds change, now that terminal nitrogen ends up with a negative charge. So we could shift them back, and then that would get us back to the other resonance form. But conceptually, the way you want to think about this, what it's telling you is that the terminal nitrogens are negatively charged, and the center one is positive. So this question says, which of the following oxygen anions is stabilized through resonance? So D is the correct answer. So what structural feature are you looking for to figure that out?
Double bond connected to the carbon atom. Oxygen is connected like that.
So the double bond is key. So you see the oxygen bearing the negative charge. That's bonded to a carbon of an alkene.
Okay, so it's just the double bond connected to the carbon bond. And the carbon bond is connected to oxygen.
C and A or A and C, those have double bonds, right? But the location of that double bond does not allow that negative charge to move anywhere.
So it's moving
Yeah, the location is what matters. So this carbon atom right here and that carbon atom right there are sp3. So they're not, that negative charge on the oxygen cannot get to that pi bond. The resonance form of D, we can push arrows down. So a lone pair can come down. That means we're forming a carbonyl group. And then the pi bond is going to push electrons onto that carbon 3 atoms away from the oxygen. So this is now negative.
And like, does it matter what algorithm it's like helping, or is it like specifically meant for the carbon atom?
So like heteroatoms, nitrogen, oxygen, since they have lone pairs, they can help drive this resonance. When we get into other situations, the lone pair can drive it, but you can also have resonance like with the benzene where it's just pi bonds that do it. So one thing I want to point out, like for C, even though it's not shown, that carbon has a hydrogen. And you take your exams online, multiple choice, so at no point in the semester do I see how you draw or think about things. But what students will do, if they try to do resonance with this structure, if you collapse this lone pair down, and try to think of it this way. That hydrogen atom is not going away. So now when you look at that carbon, how many bonds does that carbon have? 5. And you're not allowed to do that, because you're breaking or you're violating the Lewis dot rules. So again, through practicing these things, you have to funnel your thinking pattern correctly, I guess, because this is it's a violation of just the building blocks in attaining that neutral bonding pattern. Again, students will make things go away or add things that aren't there. That's one thing, if you're in that realm, you have to double check. Am I violating a Lewis dot rule by doing that? Another way of saying it, when we push this arrow down right here, those electrons have nowhere to go. The pi bond being right there as in choice D, it's allowing you to then kick out the electrons in the pi bond because it's immediately attached to that carbon atom. So which of the following is not a resonance? We call these hybrids. So in drawing, we're representing them as different structures, but in reality, it's just one structure with how we're assigning charge or where electrons are located. So B is not. So because we're showing this H atom shifting. To draw the resonance arrows for the other ones, we're just shifting the pi bonds around. For C, notice like C only involves 2 atoms and not 3. So this just comes down. That means the oxygen ends up with the positive charge. And then D, we have 1, 2, we have 4 total carbons, but for resonance, we're either only concerned with 2 or 3 atoms at a time. Since we're dealing with a positive charge, we're showing the pi bond move. So curved arrow means electron movement. So that either means a lone pair of electrons or a pi bond. So it would be improper to do this to show like an arrow starting from that positive charge somehow. So something like that. Because as it's defined, the curved arrow is showing how electrons move. A positive charge is just a deficiency of electrons. So something has to go to it.
So basically it's B because there is no change in the structure. So like there is no resonance that occurred.
Well, it's this specific hydrogen atom. It's showing it move from one oxygen to the next.
Okay.
You can't break, like,
Okay, off.
right.
Okay.
So we have about 7 or 8 minutes left. So I think we can run through this slide, which is a little bit more complex molecular formula. And you'll see, based on those heteroatoms, like the number of constitutional isomers you can draw for just that one molecular formula is going to be quite a bit. I'll walk you through the logic, and we'll see how many we can start drawing, but it's not going to be all of them. And then I'm going to try to fold in these concepts of formal charge and resonance as we draw these, point out where it could occur. So first thing we want to do is figure out degrees of unsaturation. So we scan, we see nitrogen subtracts, oxygen does nothing. So for our fully saturated, that should get us to C4H10. So that's 1 degree of unsaturation.
I have a question. How did you get the hydrogen to like hydrogen 10? Is that like when you added the nitrogen to it? Oh yeah, the
So we're just plugging it into there.
okay.
So that 1 degree of unsaturation, you're either going to have just a pi bond or a ring. So I call these the Willy Wonka problems because now we can really start using our imagination to propose things. So there's 4 carbon atoms. And now we have to put say we want to use a pi bond. So we've used our degree of unsaturation. And now we need to put the heteroatoms in there. So what can we do? Like, think of some of the functional groups we know. And the functional groups have to be saturated. We can't have any pi bonds or rings because we already used it. So if I said NH2, and then I said OH, OH. Say I didn't want the pi bond to be an alkene. Say I wanted it to be a carbonyl. So that's the pi bond. Now I'm going to make an amide. Then I need 2 oxygens. And then once you start doing this, what you can practice is, naming these functional groups. So this would be a primary amide. This would be secondary alcohol. This would also be a secondary alcohol. Yeah.
On the first structure, how did you know where to put the pi bond? Like, why did you put it in the end, like, into the nitrogen?
So the question was why. Again, I'm riffing up here. So say you don't like that. We can say we have the 4 carbons. I want to put it there, but I'm going to still keep that there and those there. So it's still a constitutional isomer. It's just move that pi bond around. The goal of this is to come up with however many of these you can that don't violate the Lewis dot rules. And then as you come up with these, you're thinking, okay, what bonding pattern does that match to the functional groups I know? And it's a way of practicing learning these different concepts.
So there's nothing like any formula that says it has to attach to carbon-carbon.
Correct. So say you wanted to make a ring instead of having the pi bond as the degree of unsaturation. So there's 4 carbons. The degree of unsaturation is now a ring. Or you could put a heteroatom in the ring. Yep.
How come on the second structure you put 3 oxygens?
I did put 3. Good call. So we need to delete that one. We'll just delete that one. Yeah, because I already used it in the carbonyl. So I violated the Lewis dot. Firing squad, have at it. But I think that's a valid thing to point out, because as you go through this, if I had to estimate, you could probably draw 30, 40, or 50 different structures for this. You have to organize it in such a way that you're not repeating something you already did or violating a Lewis dot, as I sort of added something else. So we're about out of time, but that exercise is meant to help you practice, applying the Lewis dot, naming the functional groups, and then you can go back and do the uniqueness. So your exam 1 will open up right now, and